Royal Holloway University of London, and also a deputy director of Sapiens. There's a few Sapiens people here also who probably know him very well. So you're welcome, and the floor is yours, the word is yours, however we should introduce you, so off you go.
Great, thank you very much. So as Mats has very kindly said, I am a professor of quaternary science at Royal Holloway University of London, and also one of the deputy directors of the Sapiens Centre of Excellence here in Bergen, which of course is a Norwegian Centre of Excellence. So what I've tried to do with today's presentation really is to give an overview of what luminescence dating is, what it does, and then try and illustrate some of those points by using 3 different archaeological sites that I've worked on in Africa to try and understand the way you can go about using luminescence dating to answer archaeological questions. And once or twice in that discussion we'll come across points that you can't answer, questions that you can't answer using luminescence dating, and I think that also is something that is worth considering. So this is the presentation outline. First of all, I'm going to talk about the technique itself, try and introduce that, and then I'm going to talk about 3 different sites. The first is Blombos Cave, and what I want to do there is really demonstrate that you can use luminescence dating to understand something about the archaeology which isn't just the date itself. So one of the nice things about Blombos Cave is it's a relatively early study of using luminescence dating to understand site integrity, to demonstrate site integrity. Secondly, I want to talk about Pangi Saidi in Kenya, and essentially the way in which you can mix various different dating techniques, radiocarbon and different types of luminescence dating to produce a long chronological sequence to try and understand the way that the archaeology there is evolving over time. And then lastly, I want to talk about something slightly different, which is essentially dating surface archaeology using material that's been fired, and there I want to use an example from the Bolivian Sahara. And hopefully these 3 case studies will give you a feeling for the range of things that you can do with luminescence dating. So, at its most basic, luminescence dating is a technique which allows us to date the last time that mineral grains, typically sand-sized mineral grains, were exposed to sunlight. So that's the thing that we're getting an age for when we use this technique. And the idea here really is that when sand is buried, in a sand dune in this case, or in an archaeological site, it's no longer exposed to sunlight, it's shielded from the sunlight, and that sand begins to store up energy from exposure to environmental radiation. And sunlight exposure of the mineral grain, subsequent sunlight exposure of the mineral grain, erases that record of previously absorbed dose. So this is why sunlight exposure is the thing that we are dating when we do luminescence work. And that gives us the basic age equation for luminescence dating. So the age in thousands of years, it's a relatively imprecise technique. We're pretty much always going to be functioning in units of thousands of years, not tens of years or hundreds of years. The age in Ka, thousands of years, is the absorbed dose in grey, so the absorbed radiation dose, divided by the environmental dose rate. And that basically is an iteration of all age equations. All age equations in numerical dating techniques are amount of change divided by rate of change. In the case of luminescence dating, we're looking at the amount of radiation that a mineral grain has absorbed divided by the rate at which it has absorbed it. So the absorbed dose is determined using luminescence measurements, and we'll come on to why they're called luminescence measurements in a minute. And the environmental dose rate is measured directly in the field or inferred from measurements of radioisotope concentrations, so measurements of uranium, thorium and potassium concentration. And I'm going to talk about that first just quickly. It's worth bearing in mind, each of these measurements are equally important in terms of producing a decent luminescence age. So you need to know both of these reasonably well to get a good age. So the environmental dose rate is theoretically the easy thing to measure. We can either directly measure the radioisotopes within our sample, so potassium, uranium-238 and thorium-232, or we can measure the radiation that comes from those radioisotopes and understand the environmental dose rate like that. And this is a picture of that latter process going on. So first of all, here we have alpha counters. They are simply measuring the alpha dose rate of samples that I've got ground up and within these counters. And here is a beta counter in a big block of lead, and that is essentially just measuring the beta dose rate of my samples. So I can measure alpha and beta directly from the samples that I bring back from the field. However, each type of radiation has a different range in sediments, so we need to treat them differently. So if this white dot here is our sand grain, the thing that we want to know the age of. Alpha particles in sediment might travel a few hundredths of a millimetre, very, very short distances. Beta particles in sediment might travel 3 millimetres, something like that. What that means is you can look at the radioisotope concentration, or you can measure the radiation directly from the sample that you bring back from the field into your laboratory, and your alpha and beta dose rates that you measure or calculate from the radioisotope concentrations, they are going to be accurate for the sample. If, on the other hand, you try and do that for gamma, you won't necessarily get the right gamma dose rate. And the reason for that is that the gamma rays come from a 30 centimetre sphere surrounding your sample, so a much, much larger body of sediment than what you might want to bring home and work on in the laboratory. And to get round this problem, we use this instrument here, which is a gamma spectrometer. Essentially, it's a radiation probe that you stick into the hole that you've just taken the sample from, and you leave it there measuring the gamma radiation that the sample's been exposed to. The reason that's important is because gamma dose rates are probably quite variable spatially. This is Vache Rivière 003, a South African Middle Stone Age site, and these are the ends of sampling tubes which I've hammered into the section. And essentially what we have here is nice fine-grained sediment, the sandy material that we want to work on to produce luminescence ages. But here we've got big chunks of bedrock. Here's another big chunk of bedrock, and that's the next slide. And this bedrock is almost certainly quite a lot less radioactive than the fine-grained sediment. So these are 5 centimetre scale bars. Here you can see that this sample is probably actually only getting about half of the gamma dose rate you might expect from the sediment, because the other half of that 30 centimetre sphere is encompassed by this large rock here. It makes a lot of sense. It's important to measure your gamma dose rate directly, as opposed to trying to measure it from the radioisotope concentration or the sample that you bring back from the field. And as an archaeologist, if there's one thing that you take from this lecture, it should be that. It's worth involving a luminescence dating specialist in your dating work early on, so they can make sure that you get decent measurements of the environmental dose rate before you actually bring the samples back to a laboratory and start to try and work on them. This piece of equipment is really useful in terms of getting decent ages, particularly if you've got relatively complex environments like this, and almost all archaeological sites are relatively complex from a gamma dose rate point of view. So that's how we go about measuring the environmental dose rate. The next thing that we want to know about is the absorbed dose, and that's something that we do with our luminescence measurements. So, a little bit of background to this. All of the radiation that I've referred to is ionizing radiation. That is to say, it moves electrons around the material that it interacts with. So ionizing radiation imparts energy to electrons which become divorced from their parent atom and trapped somewhere within the crystal lattice, within the mineral grain itself. And the trapped electron population is proportional to the total amount of radiation that that sample has absorbed, that sample has been exposed to since it was last exposed to sunlight, and the signal was reduced to nothing. Now, critically, light exposure detraps electrons. That is to say, it gives the electrons just enough energy to escape the place where they're trapped within the crystal and go back to the atom that they originally came from. And in the process of doing that, it erases the record of the previously absorbed dose. But this is a reversible process. So you can expose a mineral grain to sunlight, bury it, it builds up a trapped electron dose, expose it to sunlight again, that electron dose is released, bury it again, and it builds up a signal again. And people quite often use this analogy of a rechargeable battery to try and understand what's going on with luminescence dating. Essentially, during burial, electrons are trapped. In the analogy, that's equivalent to the battery being charged. During light exposure, the electrons become detrapped, and that's equivalent to discharging the battery. So this is very much a reversible process. So if instead of exposing a sample to light in nature, when sand's blowing around prior to being incorporated in our nice archaeological deposit, if instead we take a old sample from an archaeological site and measure it in the lab, what we're doing is causing this detrapping process, but in a very controlled manner. So essentially, when you detrap electrons, they lose energy, and that energy is dissipated as light. So essentially, light, the luminescence, that's a proxy for the number of trapped electrons that you had in your mineral grain, which is a proxy for the amount of radiation that mineral grain's been exposed to, which is a proxy for time. You're several steps away from the thing you want to know about here. So in the lab, what we do is we stimulate our sample with low energy photons, and we measure the high energy photons that are emitted from the sample. So typically, if you're measuring quartz, you'll shine blue LEDs, blue light at the sample and measure the ultraviolet light that comes out of the sample. Because ultraviolet is a higher energy than blue, you're not getting any of the reflected light, you're not measuring the blue light that you're stimulating the sample with, you're measuring the energy that's being released as electrons are going back to their original position within the crystal. And essentially, you use detection filters to make sure you don't measure any of your stimulating light, and then use a photomultiplier tube just to count the amount of light that's coming off your sample. That's your luminescence signal. And as I've said, the intensity of the luminescence measured, the intensity of the light that comes out of your sample when you stimulate it, that's proportional to the absorbed dose, which is one of the two numbers that you need to know to generate your luminescence age. So what does a luminescence signal actually look like? It looks like this. So we start off, we begin to stimulate our mineral grain, and we have quite a lot of luminescence signal at the beginning, and very rapidly that drops down to nothing. It drops down to zero, basically instrumental background. This is a measurement on an individual grain of quartz, so one single grain of quartz. And you see we get the signal down to pretty much nothing after 0.2 seconds worth of stimulation. Certainly after a second worth of stimulation, there's no signal left. That's not actually very helpful, because this doesn't tell you anything very useful at this stage. You then need to perform a whole series of additional measurements to understand what this amount of light actually means in terms of the radiation dose the sample is exposed to. And this is where the fact that luminescence is a reversible process becomes important, because we can reduce our luminescence signal down to zero, and then we can put a radiation dose in, and our luminescence signal comes up again, and then we can measure the next luminescence signal. We can keep doing that as many times as we want. So typically what we will do is we'll measure the luminescence signal from our natural sample. So this is the luminescence signal that has accumulated whilst the mineral grain has been buried in an archaeological site. We reduce it all the way down to zero, and then we will give a known calibrated radiation dose to that mineral grain in the laboratory and measure the luminescence from that. And we'll keep doing that, so keep putting a dose in, bleaching it all the way down to zero. We'll keep doing that until we've built up a calibration curve for that individual mineral grain, which allows us to interpret the amount of light that we get out of our natural sample in terms of the amount of dose that it was exposed to whilst it was buried within the archaeological site. So that's how we take a light sum, which is just a number of photons, not a very informative number, and turn it into the absorbed dose that the mineral grain has been exposed to whilst it's been buried. And this is a process referred to as the single aliquot regenerative dose technique, first published by Andrew Murray and Anne Wintle in 2000. And essentially, to get a reliable luminescence age, you're almost certainly using some iteration of this technique. This really is a field that's only been around in its current form for the last 24 years or so. What's an aliquot? Well, it's a subsample of your sample. So here we have a 9mm diameter aluminium disc, and it's just got quartz grains deposited onto the surface of that. And essentially, this one probably has about 1,000 grains on it. What you can do is you can measure all of the light that comes from this aliquot. That gives you an average signal across all the grains that you have in this particular subsample. And typically we might measure 24 subsamples per sample to give us a decent statistically representative number of absorbed dose estimates for any sample. And this is how the majority of luminescence ages are produced, using relatively large bulk samples, a large number of grains per assessment of the absorbed dose. But actually, in principle, there's no particular reason why you shouldn't look at individual grains of quartz or feldspar, which are typically the minerals that we use for luminescence dating. And actually, all of the data that I'm going to show you subsequently in this presentation are made on individual grains of quartz or feldspar, because they help us to understand more about the site that we're looking at than looking at bulk signals from a large number of grains all measured at once. So this is a instrument which allows us to fire a green laser down 300 micron wide holes, and this is a sample holder which has a 10 by 10 grid of 300 micron wide holes. And essentially you put a quartz or a feldspar grain into each of these holes, fire the laser down each of these holes sequentially, measure the luminescence that comes off it, and that allows us to make measurements on individual grains of sand. It allows us to produce ages on individual grains of sand. What actually we typically do is measure a large number of grains and build up a population or multiple populations of ages from any particular sample. And that's what's represented in this diagram here. And we're going to see a few of these diagrams, so let me just take a minute or so to explain what's going on. Each of these dots is an estimate of the absorbed dose for a particular quartz or feldspar grain. In this case, they're quartz grains. And one of the problems with measuring individual grains is that some are very bright. They give you a nice, shiny, reproducible luminescence signal, and some are very dim. You can scarcely tell the difference between the luminescence and the background of the instrument. And what that means is that we know some absorbed doses, DE, here very well, and some relatively poorly. And to draw your eye and to draw your analysis towards the grains that we know well, we've got a precision axis here. So essentially, at this end of the axis, we have very imprecise measurements, which aren't telling us very much at all. And at this end of the axis, we have very precise measurements, which are telling us hopefully a lot of useful information about the age of the material that we're looking at. So your eye is automatically drawn towards this end of the diagram where your more precise age estimates are. Here we have the radial axis, which is the absorbed dose. Quite often that's referred to as DE, the equivalent dose, but essentially that's the absorbed dose that a mineral grain is absorbed during its burial period. So higher up is older, lower down is younger, other things being equal. The last thing you need to know is the line drawn from this 0 point here to the radial axis. Any data points that sit on that line have the same equivalent dose. So essentially, everything within this grey bar here are equivalent doses that are consistent at 2 standard errors with the mean for this particular data set. So essentially, if you've got a data set that looks like this, all of the equivalent doses are about the same. That's telling you all of the grains are about the same age, and we don't really have a major problem here. If, on the other hand, they're scattered all over the place, large range of equivalent doses, we've got a very mixed sample, and we potentially need to think about mathematical models for pulling those apart and understanding more about them. Okay, so we've got the age equation, we know how to work out the absorbed dose, we know how to work out the environmental dose rate, so we can produce luminescence ages. What can we do with this? Well, we can work on material that's either been exposed to light prior to deposition, immediately prior to deposition, or has been heated up to about 350 degrees C during the event of interest. The material's got to contain sand or silt size quartz or feldspars, but most things do to some extent, so that's not really a major problem. And we can work out ages in the range from about 0 to 150,000 years for quartz, and maybe 0 to 300,000 years for potassium feldspar. So this, on the face of those 3 points, is a brilliant dating technique. You can date almost any site in many time frames that we might be interested in, and hopefully that should make it very useful. The problem, and the reason I say there are some types of archaeological questions you cannot answer with luminescence, is this last point. The precision of any given luminescence age is something in the region of 5 to 10%. So 10%, 100,000 years, plus or minus 10,000 years. Those are quite big uncertainties. So once you step within those uncertainties, you begin to come across types of questions that can't be answered using this technique. And most of those uncertainties are shared. That is potentially a good thing or a bad thing depending on the type of analysis you're doing, but if you're trying to use lots of luminescence ages and use a Bayesian age model to try and increase the precision, that really hampers you because Bayesian age models can't do very much with shared uncertainties. But we maybe think about that a little bit later on. So that's how luminescence dating works. The next thing I want to do is to talk about some work that was published in 2002, not work done by me incidentally, on Blombos Cave in South Africa. This is one of the sites that the Sapiens Centre of Excellence is still working on. So Blombos has been held up as a key site for understanding various aspects of the evolution of human behavioural modernity. Essentially, there's a whole series of types of behaviour, types of material culture that first turn up at this site and begin to document, to tell us about the kind of process of becoming, to some extent, the process of becoming human. So we have these engraved ochres here, very early abstract representations within the archaeological record. We've got heat-treated, pressure-flaked tools, about 73,000 years old, and we've got this abstract drawing. Somebody has kind of drawn these lines onto a piece of rock. Again, luminescence dated to about 73,000 years ago. But the piece that really put Blombos on the map is this one here, this piece of engraved ochre, this piece of engraved ferruginous rock. And the reason for that is that this is about 70,000 years old. And in 2002, when this publication was published, it was thought that the earliest abstract representation in the archaeological record was about 40,000 years younger than this and found in Europe. So all of a sudden, this site had changed both the location of where abstract art was first found, but also put its history back 40,000 years into the past. And because there were those two big changes in the way that we thought about human behavior, human symbolic representation, there was quite a significant resistance to the idea that this artifact could be as old as it in fact appeared to be. And part of that relates to the stratigraphy of the site itself. So the uppermost layers at Blombos Cave here are about 2,000 years old. They're later Stone Age, so not very old at all. If you found an engraved ochre in there, no one would be at all surprised. That's not a major problem. You've then got an archaeologically sterile sand layer here, and then you've got the middle Stone Age levels, where this does come from, keep doing that, which range from between 70 and 100,000 years ago. Right, good. So, first hypothesis was that it's perfectly possible that actually what we're looking at here is a later Stone Age artifact that's been intruded into the older material. Say it's been burrowed in by an animal or something like that. Another possibility is that we had the walls of the cave disintegrating and putting geologically old sand grains into the archaeological deposits. So actually that would make these archaeological deposits look older than they were because you're measuring a mixture of young archaeological sand grains and geologically old sand grains that had come from the cave wall. So the way of testing both of these hypotheses is actually just to look at the ages of individual grains from the site. And that's what my colleague Zenobia Jacobs did, and that's what this paper is all about, which is essentially the use of single-grain luminescence dating techniques to understand the stratigraphy of the site properly. So essentially, what we can do is we can measure lots of mineral grains from any particular deposit, and we can look at the distribution of the ages, look at the distribution of the equivalent doses from those grains, and try and understand what that's telling us about the site. So if, for example, we have a distribution that looks like this, basically all the grains are pretty much the same age, we can use the central age model, which is essentially a weighted mean, and generate an age from them like that. If, on the other hand, we have clear populations of grains at different ages, then we know we've got some kind of mixing going on. Actually, this is an artificial mix. I artificially mixed together a young and an old sample to make the point. But clearly, you can use this technique to detect mixtures of young and old material, and that potentially is what you might expect to be going on at Blombos if this archaeology is younger than we thought it was. So when my colleague Zenobia Jacobs looked at sand from this archaeologically sterile sand layer that lies between the 2,000-year-old later Stone Age levels and the 70,000-year-old Middle Stone Age levels, she found that all of those sand grains were about 68,000 years old. There's no evidence in this diagram here of very young grains, which you might expect if the artifact had been burrowed in from above, so it would incorporate some of the later Stone Age material into the Middle Stone Age levels. And there's no evidence for older grains up here either, which you would expect if the age is being made artificially old by material coming off the walls of the cave, geologically old material coming off the walls of the cave and being incorporated into the archaeology. So this sand layer is 68,000 years old with no evidence of older or younger grains. Now, if there's no older or younger grains in here, certainly if there's no younger grains in here, that means that material cannot have been intruded into the Middle Stone Age levels from above, because they would have brought younger grains with them. We also can look at the distributions from the Middle Stone Age levels and see that most of them look like this as well. Not very much evidence of erroneously old grains being incorporated from the cave walls. So that demonstrated really quite clearly that these Middle Stone Age levels really were 70,000 years old, and abstract representation in the archaeological record really was African and 70,000 years old. Fine. So they'd used single grain work to demonstrate the integrity of the site stratigraphy. That said, when Zenobia looked at some other samples, she did find examples both of contamination from overlying materials and contamination of older material, so probably roof spore from the cave walls. But you can see this, and critically, you can look at those data sets, you can make archaeological or geological arguments as to why you should accept a particular population from this data set, and therefore build up a sensible, trustable chronology for the site. That's worth bearing in mind. There does need to be a reason why you might have these different populations of grains before you can start separating them out and saying things about them. You can't just say, I don't like that one, and therefore we're going to get rid of it and just calculate the age from these red points here. You need to have a feeling for why you might be getting the patterns that you're observing, and that does occasionally catch people out. Okay, so this study pretty much set up single-grain luminescence dating as one of the default ways of dating archaeological sites beyond the time frame of radiocarbon dating. And what I now want to talk about is how I went about doing that at a site called Pangi Saidi in Kenya, and how I very nearly got it wrong. Well, actually, I did get it wrong, and then remediated the problem afterwards. So this is a Middle Stone Age to Iron Age site. So it's an archaeological sequence that is more or less continuous, covering about 80,000 years. So that's a long time. That's a good length of record to have. And the site's kind of reasonably well known for a couple of things. There's been a lot of work done on the Middle Stone Age to Later Stone Age transition, trying to understand what the nature of the change in the archaeology is. And you can do that if you have a more or less continuously deposited site that covers that transition, which Pangi Saidi has. So there's been some work done on that, and somewhat later there is also potentially the earliest intentional burial in Africa, again from the Middle Stone Age levels, so from the deeper levels within this site. So the first work that I did on this site was trying to understand the age for this very long 80,000-year-old sequence, and we used a combination of radiocarbon and luminescence dating to do that. And essentially we used exactly the same technique as I've just been showing you for Blombos Cave, measuring lots of individual grains of quartz and generating age distributions from the resulting data sets. So the first attempt, which we published in 2018, I used quartz primarily because it's much more abundant than feldspars in the majority of situations. The luminescence signals reset much faster by sunlight, which means you don't have to make assumptions about how long the mineral grains have been exposed at the surface before being buried for. A few seconds will completely remove the luminescence signal from quartz. A few days might be required for feldspar, so it's a fundamentally different requirement to fully reset the age signal. And also, at least when I was doing this work, single grain work on quartz was rather better established than single grain work on feldspar. So I measured lots of individual grains and got really quite a high yield of usable grains. 6.2% of the grains that I measured gave me useful luminescence information. They're a bit scattered, so the overdispersion of the data sets is about 24 to 34%. Overdispersion is the scatter of the data set over and above what you would expect based on measurement uncertainties. So essentially it's the scatter of the data set that results from stuff that's going on in the geology, in the absorption of dose itself, as opposed to your measurement of the absorption of dose. 24 to 34% is quite high, but if you look at the data sets, there's not much evidence that we have individual populations in there, so we felt it was an appropriate thing to do to take this central age model, essentially a weighted mean of the data that we generated, and calculate ages like that. And so we produced a Bayesian age model, which essentially incorporated these 8 radiocarbon dates with 6 luminescence ages, and produced what we thought was a really nice chronology for this site, spanning actually from about 400 years up to 78,000 years. And that gave us a really nice long sequence where we could study the evolution of the archaeology that was found at this site. So far, so good. However, at the base of the sequence, a burial of a 2.5 to 3-year-old child was found, which we eventually published in 2021. But essentially, this is where I pretty much made a mess of things. So the burial was from layer 19 of the site, so beneath the base of this chronology that we have here. But it was fairly obviously, from the stratigraphy of the site, fairly obviously intruded from layer 17, which had an age of about 74 plus or minus 5,000 years. We had a luminescence sample from within the burial pit itself, so I dated that using exactly the same techniques I'd applied to all the other samples from this site. We produced a new Bayesian age depth model. We got an age for the burial of, again, 75 plus or minus 4,000 years. So that's a little bit younger than, or quite a lot younger than some of the burials from Israel, but contemporaneous with or older than other African burials. So clearly we seem to have the oldest intentional burial in Africa. We wrote a paper, sent it off to Nature, and everything went well until we got the reviews back, at which point I had to go and lie down for a bit because the reviewer really didn't like the way that I dealt with the data set. And to give you an understanding of that, we've got to go under the hood, go under the bonnet of luminescence dating a little bit and see what's going on there. So we've known for a long time that when you measure individual grains of quartz or feldspar, actually most of the grains don't give you any useful information. And so the field has developed a set of rejection criteria which allow you to get rid of data which are not meaningful, not telling you anything very useful about the age of your site. And most of these are fairly mechanistic and uncontroversial. So you'll find that most single grain papers somewhere in them have a table like this, which tells you the number of grains that were measured for each sample, the number of grains that were rejected, and the number of grains that you used to calculate the age. And one of the things that you will notice is you measure a lot more grains than you accept. And that's particularly true as we go down to the deeper levels of this site here. So I measured 3,000 grains from the burial and only actually accepted 85 of them. Now, most of the reasons you get rid of data are, as I said, mechanistic and uncontroversial. This one essentially boils down to there's no signal from mineral grain. If you don't have any signal, you can't generate any useful information from it. This is a measure of reproducibility. Essentially, you measure the same radiation dose point twice, and if you don't get the same answer, you're not getting reproducible signals. You can get rid of that data too. This is a test for whether you're looking at quartz or not. This is a test for whether your luminescence signal is actually capable of being bleached all the way down to a 0 level. And essentially, nobody would really argue with any of these points. What tripped me up was this one, signal saturation. One of the things that happens with luminescence dating is that the signal grows quite rapidly initially, and then it flattens off, it plateaus out. There comes a point where you can't put any more or you don't get any more luminescence out of a sample, no matter how much radiation dose that sample absorbs. So signal saturation occurs when grains are undatably old. And one of the things that you notice is the number of grains are rejected because they were saturated increased as the samples got older. So essentially the layers increase in age with number, and the number of grains are rejected on the basis they were undatably old also increased with older samples, which is kind of what you might expect. So this is the shape of the luminescence growth curve. This is essentially how the luminescence signal grows with increased absorbed dose. And we fit these curves with this equation here. Don't need to worry about that too much, but essentially the point is we measure the natural luminescence of our sample. Typically we then plot that in the y-axis. That's just a convention. It allows us to understand roughly where that point might sit on our growth curve. Plotted in the y-axis, read across onto the x-axis, and that tells us the amount of radiation that particular mineral grain had been exposed to. That allows us to calculate the absorbed dose. And of course, here there's no problem. Our natural signal intercepts onto this growth curve at a point where you've got clear change with increasing dose, and so you can be reasonably happy that you're getting a sensible measurement. Now, the shape of this curve is controlled by two components in this equation here. Imax, which is the maximum luminescence intensity possible, essentially the point at which the growth curve goes flat, and D0, which is the rate at which the signal reaches that flat point. Both vary from grain to grain, and they vary a lot. You can get a big range of those values in quartz. But it's D0 that matters, because that controls the rate at which we reach this flat part in the growth curve. And I can demonstrate that for a sample with an absorbed dose of 50 grays and an Imax of 2.7. If our D0 is 100 grays, then we've got a growth curve that's still growing very strongly at, 150 grays, no problem. We're getting a good intercept on the growth curve here. We can generate a nice measurement. If you halve D0, again, still pretty good. Everything else has been kept constant, but you see the shape of the growth curve has changed just because you changed that curve fitting parameter D0. So now the equivalent dose, the absorbed dose, is the same as D0, but again, we'd be pretty happy with that as a measurement. halve D naught again, and you see the growth curve is going quite flat at relatively low doses, and the absorbed dose is about twice the D naught value. You'd probably be reasonably happy with that as an intercept on the growth curve, but you wouldn't have to go much further up the growth curve to be a bit worried about the precision of the data that you're generating. And if we halve D naught again, very clearly our natural luminescence signal is consistent with the saturation of the grain. That is to say, we don't really know how much radiation this grain has absorbed. And you can see that if you just plot the upper and lower uncertainty terms on this natural measurement onto the growth curve, they look like that. The lower uncertainty term gives you a finite value, the upper uncertainty term gives you an infinite value. So clearly this grain is saturated. How do we define, or how do we work out what other grains are saturated when the situation isn't as clear as what we have here? Well, for a long time, the luminescence community fudged this, and we did it with statements like this: saturated grains were rejected. Well, what does that actually mean? In practice, that's neither objective nor reproducible. It probably boils down to grains I didn't like were rejected. Now, obviously, use a judgment. You employ a specialist to do something like this because they've got a lot of experience of looking at these types of data, and they will probably do that fairly well, but it's certainly not objective, and it's certainly not reproducible. And one of my colleagues came up with a solution to this problem. She said, well, look, we've got this growth curve fitting parameter, D naught, and that defines how rapidly our growth curve goes flat. Why don't we just get rid of data where our absorbed dose that we calculate is more than a certain number of times the growth curve parameter which defines this saturation point? And she said, arbitrarily, why don't we get rid of all grains, or all aliquots, where the absorbed dose is greater than 2 times this D naught curve fitting parameter? And just to illustrate what that might look like, this is an absorbed dose that is exactly 2 times the curve fitting parameter for this curve. Essentially what she said was, up to that point in the growth curve, we will accept grains, but beyond that point in the growth curve, we won't. And that makes sense. It's objective, it's reproducible. You would expect 2 users to get exactly the same answer. It's also completely arbitrary. I mean, why not 2.5 times D naught or 1.5 times D naught? 2 just seemed about right. More importantly, it's biased. You're automatically cutting the older grains out of your data set, and therefore potentially you're biasing the age that you calculate to a younger age than the true age of the sample. That said, in 2018, when we first published this data set, this kind of technique, this idea had been patchily but moderately securely adopted by the community, and so I'd used it to produce the chronology for this Kenyan site. However, the review of this paper made the point that because this approach biases the mean age towards younger values, and actually it's quite difficult to measure D naught accurately anyway, I was potentially causing problems with the data set, getting erroneously young ages for this child burial. And what the reviewer said was, actually what you need to do is you need to go away and remeasure those samples, and instead of using quartz, you need to measure feldspar. Why would we measure feldspar? Because feldspar is capable of absorbing much larger radiation doses than quartz. It's capable of going back at least twice as far in time as quartz, and therefore we get around this problem of having undatably old mineral grains within our samples. There are a number of problems with that approach. Feldspar bleaches, that is to say the luminescent signal is reduced much, much slower than for quartz. So you could have a problem whereby your feldspar grains weren't exposed to enough sunlight to get rid of their luminescent signal prior to burial, so you could get an erroneously old age simply because the sample hadn't seen enough sunlight prior to being deposited. Feldspar luminescence properties can be a bit inhomogeneous. Actually, they weren't at this site, not a major problem. a big problem that we had at this site is there's really not very much feldspar in it. So there was much more quartz, which is why I started working on quartz in the first place. There is also the fact I'd never worked on feldspar before. And the reason for that was actually a good way of measuring feldspar has only relatively recently been demonstrated. So we've known how to measure quartz since 2000. Realistically speaking, we've only known how to measure feldspar for the last kind of 5 to 10 years. And so actually, it wasn't my kind of go-to tool when I was dating a new site. So this makes the point about feldspar being a better mineral for older grains. So here we have two different growth curves, one for quartz, one for feldspar, both going up to the same dose, but clearly you've got much more growth left in the feldspar curve at 200 grays than you have in the quartz curve at 200 grays. And this is why feldspar can take you back much further in time than quartz can do, other things being equal. So when I did that, all of the D0 values for the feldspar grains I measured were much larger than for quartz, and no grains were undatably old at this kind of 75,000-year-old age that we thought we had for the child burial. So, after several months of work, so I was basically learning this one on the job, we produced these four feldspar luminescence ages and compared the ages that we got when we produced the new Bayesian age model. And the answer is, the two ages are within uncertainty, and actually the feldspar age is less precise. So an awful lot of work to get pretty much the same answer. But we now knew that this answer was right, whereas with this one there was always going to be question marks over whether the data were giving us a useful answer or not. And actually, increasingly, if you really want to fully understand what's going on at a site, if you really want to be secure about the chronology of a site, it's worth getting both quartz and feldspar work done on the site. Because if you end up with the same answer for those two different minerals which behave very, very differently, then the chances are you're looking at an accurate age for the site. And I guess it was worth all the effort in the end, because we got the paper in the front page of the cover page of Nature, and it's a really nice study. It's a really nice site to have a good chronology from. So I guess my point here is that for a long time we've thought about quartz as being one of the main kind of ways of dating an archaeological site. Actually, if it's really old, you can push the time frame back further by using feldspar as well, both overlapping and then using feldspar as your main chronometer as you get to older deposits. Fine. So the last thing I want to talk about is a slightly quirky use of luminescence dating, trying to understand open-air archaeology, so essentially archaeology from deflated surfaces in the desert of the Libyan Sahara. So, when you just kind of stand somewhere, almost anywhere in the Sahara, it appears to be full of nothing. There's a whole lot of not very much going on in the Sahara until you start looking at your feet, and then you see there's archaeology all over the place. So here we've got a quern and grinding stone. Here we've got a grinding stone. Here we've got a cow tethering rock. You can see chunks have been taken out of either side of it to allow you to attach a rope to it. Bits of pottery, bits of ostrich eggshell. There's stuff all over the place in the Sahara. The problem is almost none of it is dateable because the soil that it was deposited on or in has been blown away. There's very little radiocarbon dateable material. Very often the bone's been destroyed by abrasion by the sand. Occasionally you get the occasional bit of dateable ostrich eggshell, but there's not much to date at these types of sites. And yet there's lots of archaeology there. So how might you go about doing that? Well, one approach is to deal with the fact that luminescence can be reduced by exposure to sunlight, but it can also be reduced by heat. If you heat a sample up to about 350 degrees C, all of the luminescence is gone, and it will begin to build up a new luminescence signal that accumulates since the point of heating. And that's not very useful in the majority of situations because not all that much archaeological material gets heated up to that kind of temperature. but rocks within hearths do. And this is a pretty typical, this is a pretty typical Saharan hearth. That is to say, there's a mound of fairly obvious burnt rock sticking out of the landscape. Now, I've been told that the figures I'm about to show you are not particularly well drawn, and that's right, but hopefully they do illustrate the point. Essentially what's going on here is that these hearths were constructed as pits within the soil. So people dug a hole into the soil, they lined it with rocks. This is the bit that nobody likes. Had a fire in it, that heated all of the rocks up to a nice high temperature and reduced the luminescence to 0. But then at some point the hearth is abandoned. The Sahara used to be a lot wetter than it is now, so the Sahara dried out. The soil surrounding those hearth rocks was blown away, and you end up with topographic inversion. You end up with the hearth rocks that were buried in a pit actually protecting the underlying sand and soil and producing these raised features that we see here. So essentially that's what's going on there. This is quite a big one. Most of them are much smaller. Most of them are much more like this. But you see them all over the Sahara, all over the Arabian Peninsula. Holocene archaeology does seem to largely consist of piles of burnt rocks in these deserts. So, heat the sample up to 350 degrees C. It removes the luminescence signal just as well as sunlight does. So it should, in theory, be possible to date the last firing of this hearth using luminescence, which gives you a chronology for the surrounding archaeology, which is hopefully associated with that hearth, which is otherwise undateable. So, this is some work I did quite a long time ago now at a site called Al Wafa in Libya, which is a pretty typical Saharan hearth field. There are kind of 200 plus of these hearths just in a basin in the Sahara. And the parent material for these hearthstones is something called the Brack limestone. So it's a lacustrine limestone. It's got an awful lot of quartz grains with it, sand-sized quartz grains within this lake limestone. And it's old, properly old, greater than about 200,000 years old. And all of these sites are associated with Epipaleolithic artifacts. Yes, another one of these hearths. The Brack limestone is quite a good substrate for this type of study because it's old, so we should be able to tell the difference between the very old bedrock that has been burned and burned material that's had its luminescence zeroed and then built up a luminescence signal subsequent to the firing event. It's also a good substrate because it's a limestone, which means instead of removing the outside of the rocks with a chisel or something like that, I can just put the rock into hydrochloric acid. It'll eat away at the limestone and it'll remove the outer portions of the rock and leave me the inner portions of the rock to work with. So essentially what I did was I sequentially hydrochloric acid etched off the outside of these blocks until I got towards the middle of the block, which should have been fully shielded from sunlight since firing by the outer material which I've now etched away. And of course, if you look at single grains, if you look at individual grains of quartz, you can demonstrate that that's going on because you can look at the dose distributions of each layer and demonstrate that you're getting fewer and fewer grains that have been exposed to sunlight at the outside of the block. So, I did this sequential etch, removing about 2 to 3 millimeters of the outside of the block in each etch and measured an age for each of them. And essentially, this is the data set you get. So this is 0 depth, the outside of the block. This is 25 millimeters depth, the inside of the block. And this is the absorbed dose that I measure from each of those sequential etches. So the outside grains have a measurable equivalent dose of a couple of grays, but clearly it's quite young. You go to the next etch in, and you get a higher value. Next etch in, you get a higher value until you get a plateau towards the center of the rock. Those grains were fairly clearly zeroed by heating when the hearth was last used, but have not been bleached by sunlight exposure in the subsequent however many thousand years that rock has lain around on the Earth's surface in the Sahara. So essentially what we did was for all of these rocks was we kept going towards the middle of the block until we got a very clear plateau, and then we used that plateau to calculate our equivalent dose for the sample and therefore our age for the firing of the sample. And because none of these hards had any dateable carbon in them, I wanted to demonstrate internal consistency for the data set, and so I measured 3 rocks from each of these hards. And here we now have nothing on the x-axis, age on the y-axis. So this is the first half, my 3 different age estimates and my mean value. This is the second, and this is the third. Nice and internally consistent, suggesting that all of these hards within the Al Wafa Basin were last used between about 7,500 and 8,500 years ago. That actually makes sense, because between about 12 and about 6,500 years ago, the Sahara was relatively wet. We know that there was at least kind of savanna grassland in this part of the Sahara, perfectly reasonable place to be herding cows, perfectly reasonable place to be gathering grains off the landscape to turn into bread or whatever. So entirely consistent with the archaeology that we have at these sites. And all of a sudden we have a method for dating surface archaeology which was previously thought to be undateable. And I hope this kind of illustrates a slightly quirky, slightly different use of luminescence dating to answer an archaeological question. And that's it, really. Those are the 3 things I wanted to tell you about. Hopefully it made sense.
I'm just going to turn on the microphone here. Thank you so much, Simon, for an illuminating presentation. I'm sure there are lots of questions there. I have some probably quite basic ones. I'm a bit curious about the human component in conducting these analyses. How large would you say it is when compared to, for example, radiocarbon dating? How much do you actively have to get involved in reading and arriving at these results?
Right. So that's changed over time. So when the first Blombos cave work was published in 2002, we as a field were kind of struggling towards understanding what grains you should be getting rid of, so what grains you should be rejecting, and refining rejection criteria. So I think back then there was quite a large human component to it. Different people were doing different things. And in fact, Zenobia Jacobs, who did that work on Blombos in 2002, subsequently published a paper where she analysed some data sets, and she got a couple of graduate students to analyse data sets, and they looked at the differences between the results that they got. So I think relatively early on in the evolution of this technique, there was quite a large human component to it. By the time I was working on the Panga Saidi material, particularly by the time I worked on the feldspar material, there's a whole series of R scripts that are available more or less off the shelf for analysing these types of data set. And actually there's now no human component in working out what grains you might accept once you've set up the parameters that R is going to work with. So in that sense, which grains you accept and incorporate into your age estimate is now completely mechanistic. And that's a good thing, because it used to take comfortably a day and a half to go through a single grain data set for a single sample and accept and reject by eye or using various different criteria the individual grains. So now you can just get R to do it for you in 10 minutes or so. There's still a human component in interpreting the subsequent distribution of acceptable grains. So the point at which you say, okay, I can see that there is a good reason for thinking I can use a weighted mean to generate an age for that sample, as opposed to mathematically deconvolving different populations and using one of those populations to produce an age, that's still going to be the judgment of the person doing the work. I think as time has gone by, we have become progressively less tolerant of people pulling apart, mathematically deconvolving data sets and just using one part of it to generate an age without really good justification than we were at first. So I think 20 years ago, we might have been much more comfortable with people using the finite mixture model to deconvolve different age populations and then say, that's the one we're going for. Now I think you'd have to have a really concrete explanation for why that was the appropriate thing to do.
All right, thank you. Do we have any questions from any of the audience members yet? Yes, we have one over here.
Yeah, one thing that I really don't understand is the fact that you have individual signals of different quartz grains. They behave different. And I've really never seen a really good explanation why they behave so different.
So, in a sense, why does it matter? Luminescence is fundamentally a phenomenological technique that you deal with what you have, not what you should have. So the reason you might have different shaped growth curves, for example, must boil down to the number of traps that you have which are capable of accepting electrons, and the number of places those electrons could subsequently go which would produce light. So that will boil down to the geochemistry of the individual grain, imperfections within that individual grain, and probably also its history of heating, cooling, and cycling through the environment over time. So that will vary very strongly from one different grain to another. But in a sense, whether it matters or not, except in the sense that for some types of samples you're going to have to measure many more grains than other types of samples, I'm less sure about that.
But to some degree it matters if you, as you know, I mean, our bedrock here in Western Norway is apparently not good because luminescence is not working well on this here, and I've heard different explanation. It has something with the electron traps that are mature, and it's better when you have sedimentary bedrock, but I haven't really seen a good physical explanation other than saying that makes sense. I mean,
yes,
it's something you can measure, something you can see.
People have tried to look at geochemical impurities in individual grains and not really come up with good, hard and fast explanations. So people have looked at that to some extent, but I do think the answer to this boils down to the fact that it doesn't actually matter that much so long as you can identify the grains which are and aren't giving you usable information. But, sorry, it must boil down to the density of electron traps and places that can produce luminescence.
When you're heated them, and I find that interesting, because one of the problems in Western Norway is that they don't find much organic material for the oldest sites. And I'm thinking potentially a method would be, as you're saying here, for exposed, when you have fireplaces. And what kind of material would you expect that you could date from an open air early Mesolithic site, for example?
In principle, anything with quartz in it. Feldspar behaves slightly. Quartz tends to get better when you heat it up. Feldspar tends to get less good when you heat it up from a luminescence perspective. So I think I would want to have something that had a reasonable amount of quartz in it.
Would you get a signal in flint?
Most flints don't have an optical luminescence signal.
No.
So you could measure thermoluminescence, where you get the luminescence out of the sample by heating it up as opposed to shining light at it. That does work, and that is actually fairly routinely done on flint artifacts in archaeology, but flint doesn't have an OSL, an optically stimulable signal.
Not right.
Normally.
No.
All right, one question back here.
Yes, thank you. Just first a comment for the previous discussion and then a question. So we actually had one master student working with some site called Nilsvika Bjorøy here in Western Norway some years ago, together with Helena Alexandersson in Lund at the laboratory. And one thing we first thought was that the quartz would be really bad, and we had a problem. We also worked with the feldspar in that site. But actually, on that archaeological site, the quartz were really, really good. So we had a paper at INQA discussing a little bit about the archaeological context, and actually that there are things happening on archaeological site that makes the quartz being better. But we cannot really explain it. But that was just a comment. And
Firing could be that.
Yeah, and also walking and trampling, and there are lots of So and that's a master thesis that is available for to read. But one other question is, and perhaps it's not in your field, but what about the portable OSL detectors? How do you think they could play part in the archaeological fieldwork, for example?
So what a portable detector can do is it can show you patterns but not absolute values. And that would have been immensely useful on geological fieldwork I was doing in Libya, because I spent an awful lot of time bringing back saturated samples, and you would be able to tell that with a portable reader. People have used portable readers to look at changes in signal intensity through a site to see where they might have stratigraphic breaks, to see where you might have, you know, a young block of sediment and an old block of sediment. And I think there it's very helpful, because a luminescence age takes quite a lot of time to produce. And so if you can use the portable reader to understand where the breaks in your stratigraphy might be, and then you can use conventional luminescence dating to pin down what the ages of those are, I think that would make a lot of sense. I don't have very much experience of using portable readers, but people are doing interesting stuff, both in terms of understanding the initial kind of nature of the site, so that kind of stratigraphic context I've just been talking about. You can also see when things change in terms of the material that's going into your site, because you can see changes in the sensitivity, changes in the amount of luminescence per unit dose that a sample is giving you. And that very often tells you something about either dilution via organic material or a change in the source of the material that you're actually measuring. And again, that could potentially be useful to you. But you're never going to produce, or at least I don't think you're ever going to be able to produce ages using a portable reader. You're always going to be looking at patterns of change.
Thank you.
Any other questions from the audience? Has your ratio, the larger than 2 times D0, become a standard yet, or is it a standard?
No, exactly the opposite.
The opposite.
So it was that got me in trouble,
right,
with the Kenyan site. So I think for quite a long time, people either did it by eye, so they went, I believe there's a good reason why I can believe the data I'm getting from that grain but not that grain, or they use the 2D naught thing. I think probably between maybe 10 years or so ago and 5 years or so ago, quite a lot of work was done on understanding the effects of very old grains within a data set, and what that meant in terms of your ability to produce a useful age estimate. And that probably did demonstrate that the 2D naught approach probably wasn't great, and probably was causing people problems. So it's an interesting one. So in 2018, it hadn't really occurred to me that there was anything wrong with doing that. By the time we got to the 2021 paper, I did the same technique, because we're adding one more date into a pre-existing data set, and that seemed like there was a rational thing to do. But I think the right approach was the one that the reviewers eventually forced me to take, which was to measure something that's capable of generating larger ages. So no, I don't think the 2D naught approach is acceptable these days. What you can do is filter your data set by D naught and essentially look at the way the absorbed dose changes as you go from low to high D naught values. And what you tend to see then, and I didn't show you that from this site because it's fairly involved, what you tend to see then is that your calculated absorbed dose rises as your D naught criterion gets progressively more stringent and then flattens out. And the flat point does seem to be the right age when you measure it with a different mineral. Oh. So I think that probably is the way you would do it these days.
Right. Okay. Yes.
Could you elaborate a little bit more on the gamma measurements?
Yeah.
How important?
It can be very important. So if you think about a situation, you can have a situation where you've got a virtually radiation-free rock and a relatively radioactive matrix. And so if you take a sample from wedged right up against that rock, 50% of the gamma dose is coming from the radioactive matrix, 50% of the gamma dose isn't coming from the non-radioactive rock. Now at that point, if you measure the radioisotope concentration of the matrix and assume that applies to the whole gamma dose, dose rate, you will overestimate your gamma dose rate by 50%. And typically gamma is going to be something in the region of a third of your total dose rate. That'll vary a bit depending on the exact radioisotope composition. So you could be looking at a kind of 50% error incorporated by not having an in situ gamma measurement.
But you mentioned 30 centimeter, then you are safe, more or less, if you are 30 centimeter away from a rock.
Yes, but you can't see gamma radiation. And so you very often see people write, homogeneous environment within 30 centimeters of the sample, and I've done it myself. You don't actually know that to be the case. So there are situations where you're probably safe with that. So when people were working on Kalahari dunes, trying to understand the age of the Kalahari dunes, if you've got 30 centimeter thickness of Kalahari dune sand, it's probably all the same stuff, and you are almost certainly correct to say, if I measure the gamma emitters in my sample, that probably is a good representation of what's going on within 30 centimeters of the sample too. It's much more difficult in other situations because you don't really know what the radioactivity of a site looks like until you start measuring it.
But could you measure the sample after you've taken it?
Yes, but that will tell you the gamma dose rate of the material in your sample tube and not the gamma dose rate of the 30 centimeter sphere surrounding your sample tube.
And it can't calculate.
No. What you could do, if you had that very simple situation where you have matrix one side and rock the other side, you could take a sample of the rock and the matrix, calculate the gamma dose rates of those two, and then do a very basic mixture model to understand what that means in terms of your gamma dose rate, for the mean gamma dose rate for the sample. That's done quite a lot, and that's a perfectly legitimate thing to do, but you can't guess it by looking at it.
Just a follow-up question on the gamma rates. What about the moderation of water if it's been a sample that has partly been underwater during a longer time? That could be, for example, we have 3,000 years of being an underwater site, and then it's... how do you...
That requires informed argument, essentially. So just to give the rest of the room the background, water in a sample absorbs radiation that would otherwise produce luminescence in the sample. And so the more water you have in the sample, the less luminescence you get per unit time. So you've got to modify the dose rate of the sample according to the water content. And what you need to know is the mean water content across the entire burial period of the sample. So there are some situations where that's quite easy. Again, people started out working in the Kalahari dunes, they're pretty dry. 2 or 3% water content is probably fair enough. If you've got a saturated sample, again, you can work out where that was. If you've got a situation where it varies, where water content is likely to vary over time, you've got to work out a rational argument for what you think the mean water content of the sample will be. So when I was a postdoc, one of the things that I was working on was trying to understand the expansion and contraction of Lake Chad. And one of the sets of samples that I worked on were sand that were part of Barkhan dunes, so these little kind of horseshoe crab-shaped dunes, and that then had a lake sat on top of them, and you could see that because they had lake sediments on top of them. So when they were a dune, they were dry. When they had a lake sat on top of them, they were saturated. And it simply had to work out what the percentage water content of those two situations was, try and work out roughly what proportion of time each of those situations had occurred. And then I think critically, you do a sensitivity analysis to work out how wrong you can be in your assumptions about the amount of time that each of those two situations has occurred, and use that to generate a more meaningful uncertainty on your age. So my starting point for these things is always work out what my wettest and driest conditions are, try and understand to see whether I can come up with good grounds for making making arguments about how long each of those two situations has pertained for, and then try and work out how wrong I can be in that argument and still have a believable age. Or maybe work out what uncertainty a given degree of wrongness would cause in my age. But water content is the fundamental reason why luminescence is not very precise. And that's where a lot of your uncertainty comes from.
Andrew Murray always told us that we should aim for taking samples under the groundwater level.
Yeah.
I mean, then you are, if not safe, I mean, there we can assume that it has been stable.
Assuming the groundwater table has always been where it is now, and that water isn't moving uranium, which it will.
But as you say, because I remember this when we did this also on sites in Russia where you have thick piles of sediments, the uncertainty was many thousand years,
yes,
simply because of water content uncertainties.
Yes, yeah, water content's a pain. It's a real nuisance in luminescence dating. But yeah, that's right. A situation where you think you can guarantee either saturation or relatively dry conditions are ideal for a luminescence sample.
All right. I guess that concludes today's seminar, and I think we're going out someplace. Huh? We can try mentally. I have to pack my stuff anyway, so someone else will have to lead the way. Next research seminar is in 2 weeks, on the 3rd of May, with Marte Spangen. Title is in Norwegian, Varangermøter om transkulturell utveksling I middelalderens Nord-Fennoskandia. So I hope to see many of you then and there. And again, thank you, Simon.
Thank you.